everyone, and welcome to another video. So today we are on to week 8 of our classical control theory class. So let's take a look at the roadmap of where we're headed this week. So if you remember last week in week 7, we looked at starting to discuss PID control and looked at a couple of simple ways that you might be able to start thinking about how to design a PID controller. Well, that's what I want to look at this week in week 8 is we're going to focus a lot on PID controllers, and in fact, we're going to look at first, what are some of the practical implementation issues that you might encounter when you're trying to build and synthesize a PID controller, right? This earlier discussion last week was pretty idyllic and academic and everything was perfect. Well, everything's usually not perfect in the real world, and I would like to look at some of the issues that you might encounter dealing with a PID controller if you actually try to build a real control system around this. After we understand some of the pitfalls that you might encounter, I want to look at 2 different ways that you can use to synthesize or design a PID controller. And really, in this case, that really just means how to pick these KP, KI, and KD, as well as maybe a few other parameters of these controllers. So the first technique I'd like to look at is something, it's very popular, but it's not super duper mathematical, which is actually both a pro and a con. So this is what's known as the Ziegler-Nichols method of how to choose PID gains. So I'll let you watch this video and see how that works. You'll see it's an interesting sort of online technique that involves a little bit of trial and error, but it's a way to go about it. The more formal and probably more robust way to go about doing PID control design is to use a formal mathematical approach and use some of the root locus discussion that we had earlier. In fact, in last week, we'll bring that to bear and use this on a PID controller. So that's what we're doing. At the end of this week, hopefully everyone is, I don't want to say an expert, but everyone is going to have a pretty good handle on how to design a PID controller. And you probably shouldn't be scared of them. And that's a good reason, too, because these are some of the most popular control systems that you'll see anywhere. Okay, so that's the game plan. Is the week 8 is all about designing PID controllers. Let's take a quick look at the homework. It's actually not that bad. It's pretty short, actually. So the first problem I'd like to look at is, let's go ahead and, you remember homework 6 problem 2? And I know that's a bit of a rhetorical question because I know people probably don't. People sometimes try to forget homework as soon as they've got it completed. So let me bring this up just to refresh your memory. So remember back in homework 6 problem 2, we were dealing with this plant, and we said, let's design a controller that looks like this using root locus techniques. And we said, okay, here you can do this, and if you think about this long enough, this is about the dumbest PID controller you could have. This is just a P controller, right? It's just a proportional gain right here. So what I'd like to do is revisit this problem, but come up with a more sophisticated control scheme here. So we're going to be looking at using the Ziegler-Nichols technique to design a full-on PID controller. So for the first part, part A is basically, if you go to this link right here, this is a specific timestamp in the Ziegler-Nichols video, you'll see I show how to design, or I basically show how to get this result. And you see, all this is a PID controller for a sum plant model with different techniques using the Ziegler-Nichols method, which is really just a bunch of different PID values. And you see you get different responses on those. So all I'd like you to do is generate a similar plot to this using this plant model. Okay, so that's all part A is. To help with this, I do have a Ziegler-Nichols function that might help. So again, to find a lot of these materials and these supplemental items, just go to the video, open the description, find the link here to my GitHub page, and I provide a function right here called Ziegler-Nichols. I'll let you go ahead and read the documentation on how to use this guy, and hopefully you can bring this to bear in this homework problem, and it will help you get these PID gains. Okay, next, then let's go ahead and try to design a transfer function, a single representation of a PI pseudo-D controller using whatever you got from the Ziegler-Nichols method in part A, okay? So what you should end up with here is it's a transfer function, a second order transfer function, which is equivalent to a PID controller, or excuse me, a PI pseudo-D controller. And again, you're going to understand what I mean by the pseudo-D part by the time you watch this video over here. Okay, so what you're doing here in part B is using Ziegler-Nichols to basically get a set of gains, KP, KI, KD, as well as this parameter A that I think will make sense what it is, again, once you watch those videos. Part C involves just taking what you have here. You've designed something in Part B. It's pretty close to the mark using Ziegler-Nichols. I'd like you to load both the plan and that pretty close controller into the MATLAB Control System Designer, and then use the Control System Designer to further refine your design to improve the settling time and percent overshoot. You're going to see that what you get in Part B is okay, it's in the ballpark, but it's not great. So Part C is using a root locus approach to go ahead and design a better controller. And it doesn't have to be way, way better. Just make some small improvement to things like the settling time and the percent overshoot. Then once you have that design in the Control System Designer, I'm going to show you a workflow whereby you can then back out what the equivalent P, I, and D gains, as well as this A parameter are for your improved controller. And again, to help you with this, I have a function that will help you. So to get to that function, obviously, I listed out here, but you're going to watch this video down here in the process of the discussion. So let me pause this. And again, if you open up this video's description and come here, you'll see I also provide you another function here called extract PID gains from second order transfer function. So you should be able to use that function that I provide to take the C of S that you designed in the Control System Designer and then extract these numbers, okay? And then what you can do is just go ahead and build a Simulink system to verify your performance. That's all problem one is. It's basically using both Ziegler-Nichols and root locus to design a PID, or I keep saying PID, but really to be more precise, it's a PI pseudo-D controller. Yeah, so that's what problem one is. Problem two is kind of interesting. Problem two is looking at some of these issues that are going to arise here, again, in the practical implementation issues video. If you watch the video kind of towards the end, in fact, let me pull this over. I pulled up some near sort of the timestamps that I'm talking about. Oops, let me see if I can put these on the same screen. Well, that doesn't work super great, but okay, I think you get the idea. Anyway, watch this video around the 2 hour and 3 minute mark. We start talking about what's known as integrator anti-windup or integrator state saturation that goes by a lot of different names. And I want to investigate some of the nuances with this. So what I'm trying to show here, I want you to investigate in problem 2, part A, show that these two models, model A and model B, are not the same. And again, you can kind of see this is what I'm demonstrating on the video. So I think by the time you watch the video, you should be able to do a similar operation and just convince yourself that these two are not the same thing. And same thing with part B. A lot of the times we are very tempted to say the gain or the integrator, it doesn't matter which one goes first, but by the time you start introducing some of these nonlinearities like integrator anti-windup, now the order is going to matter. And again, I just want you to show in part B that they're not the same. You don't have to derive anything or prove anything, just put in a couple of input signals and show that you get different outputs on both of these model A and model B. And then the last part of the problem here, part C, is go ahead and let's think about if you wanted to implement integrator anti-windup, how would you do that? So just write some skeleton code. Again, this doesn't have to be functional working code, but I just want people to start thinking about what would you have to write or what would you have to do if you wanted to limit the state of the integrator as is being done in Simulink. Again, we're just thinking about what's happening under the hood when you make Simulink draw this little diagram here and say this is not just a normal integrator, it's an integrator with anti-windup. Okay, so that's the game plan and the roadmap. I think this is probably a good spot to leave it. We can make this a quick discussion for week 8 because it's pretty straightforward. It's just playing with PID controllers and looking at some of their nuances. So email me if anyone has questions. Otherwise, I'll look forward to talking with everyone during office hours again. Thanks. Talk to you later. Bye.